Hey everyone, Dr. Mungli here. So this video about fructose metabolism. How the fructose is metabolized in our body. As you all know, fructose, most of it will be coming into our body as sucrose. Sucrose is a disaccharide. It is composed of glucose and fructose, which is held together by alpha 1,2 bond. Now the sucrose, it comes from table sugar or beet sugar or cane sugar. So sucrose is broken down into glucose and fructose in the intestine by a brush border located enzyme called sucrase. Now how else fructose comes into our body? So one of the important source of fructose is high fructose corn syrup. Now the high fructose corn syrup, they can be of different types depending on what is the amount of fructose in that. Usually the content of fructose in high fructose corn syrup, it will vary from 40% to 60%. That is why it is called as high fructose corn syrup. Rest of the thing will be glucose. It's basically a mixture of glucose and fructose. Now what will happen to the fructose? So the fructose in the intestine, it will be absorbed from the lumen into the intestine by GLUT5 transporters along with the glucose. Once it gets into the enterocyte, it will go out of the enterocyte into the portal system by GLUT2 transporters. I have a video on carbohydrate digestion and absorption. You can watch that video as in the link that is given below or the link that is appearing right now in the upper right corner. Anyway, once fructose gets into the portal blood, so the fructose will be taken up by the liver predominantly. Liver is the major organ where fructose is taken in. There are other two tissues which can take fructose, and that is it can be taken up by the intestine or it can be taken up by the renal tubular cells. And there are some papers which will say that fructose can also be taken by other tissues, especially by GLUT8 transporters. Anyway, let's concentrate ourselves with what happens to the fructose, which is the major fate of fructose in our body is it is going into the liver. So who is going to take, which transporter is going to allow fructose into the liver? So the hepatocyte, it is going to express two kinds of transporter there for fructose. One is GLUT5 transporter, other is GLUT2 transporters. Now the GLUT2 transporter has got higher capacity to take glucose and fructose, although major affinity is for glucose for GLUT2, whereas GLUT5 transporter, it is a fructose transporter there. It is going to transport fructose in the liver. So once fructose gets into the liver, so what will happen to the fructose? That's the metabolism of fructose now. So the fructose, once it gets inside, so fructose is converted into fructose 1-phosphate. Fructose 1-phosphate. Fructose is converted into fructose 1-phosphate by an enzyme called fructokinase. So this fructokinase enzyme, it is going to consume ATP for that. ATP is getting into the reaction and go out as ADP, and the terminal phosphate, it is attached to the first carbon of fructose. That is why you got fructose 1-phosphate there. And the fructokinase, which is expressed predominantly in the liver, it has got high Vmax. Fructokinase is a high Vmax enzyme. It means it is going to go on converting fructose into fructose 1-phosphate as long as you have sufficient ATPs available to do that. So what is the problem with that is as the fructose is converted to fructose 1-phosphate, fructose is trapped inside the cell because it is phosphorylated. Any monosaccharide that is phosphorylated, it is just trapped there in the cell. It cannot go out. So what is the fate of this fructose 1-phosphate now? Fructose 1-phosphate in the liver, further down it is converted into glyceroldehyde, and other is dihydroxyacetone phosphate, DHAP. Now the dihydroxyacetone phosphate is a glycolytic intermediate. So whereas glyceroldehyde is not a glycolytic intermediate, it has to be converted into glycolytic intermediate. Now the fructose 1-phosphate is broken down into these 3 carbon molecules, and that job is done by an enzyme called aldolase B. This aldolase B enzyme, there are actually 3 kinds of aldolases in our body. Aldolase A, which is present in most of the cells including muscles. Aldolase B is specifically present in the liver and in the kidney, whereas aldolase C, it is present in the brain. What is the speciality about aldolase B compared to aldolase A and C? Aldolase A and C, they can specifically break down fructose 1,6-bisphosphate into glyceraldehyde 3-phosphate and dihydroxyacetone phosphate, which is there in glycolysis. Whereas aldolase B has got a speciality that aldolase B can break down fructose 1-phosphate in the fructose metabolism. It can also break down fructose 1,6-biphosphate in the glycolysis. Now, if you compare the affinities of these two molecules, that is fructose 1-phosphate and then fructose 1,6-bisphosphate for aldolase B enzyme. So, aldolase B enzyme preferentially want to metabolize fructose 1,6-bisphosphate into glycolytic intermediate before it metabolizes fructose 1-phosphate into glyceraldehyde and dihydroxyacetone phosphate. That means when both the molecules are available, aldolase B prefers to metabolize glycolysis first rather than coming into fructose metabolism. Anyway, whenever there is accumulation of fructose 1-phosphate here, aldolase B is going to break down fructose 1-phosphate into glyceraldehyde and dihydroxyacetone phosphate, and aldolase B is a rate limiting enzyme for fructose metabolism. This is a rate limiting enzyme. This step is rate limiting for fructose metabolism, and also note that this is not a regulated enzyme. It means in fructose metabolism there is no regulation. So, and also this is an insulin independent mechanism, because glucose is insulin dependent process, glycolysis is an insulin dependent process, whereas the fructose breakdown is an insulin independent process. That means, so as long as fructose is there, it is converted to fructose 1-phosphate, and that is converted into glyceraldehyde and dihydroxyacetone phosphate. Now what will happen to these two molecules? This is the fate of glyceraldehyde here. So the glyceraldehyde is converted to glyceraldehyde 3-phosphate. Glyceraldehyde is converted to glyceraldehyde 3-phosphate, and that will be done by an enzyme called triacylglycerol. Triacylglycerol, which is present in the liver. Triacylglycerol enzyme. So once you get glyceraldehyde 3-phosphate, so this glyceraldehyde 3-phosphate is a glycolytic intermediate, so it can go on to make pyruvate. So pyruvate is a glycolytic intermediate, and pyruvate later it will be converted into acetyl-CoA. Acetyl-CoA can form here, and acetyl-CoA can be diverted into fatty acid synthesis. Fatty acids, most of the acetyl-CoA is converted into fatty acid and cholesterol. So fatty acid and cholesterol can be synthesized. So that's the fate of fructose. Whenever we consume a lot of fructose along with the glucose molecule, so the fructose, it floods into glycolytic pathway all the way becoming pyruvate, and pyruvate is diverted into acetyl-CoA, and most of the acetyl-CoA is diverted into fatty acid synthesis. How that happens? Acetyl-CoA initially gets into TCA cycle, combine with oxaloacetate, becomes citrate. But once the TCA cycle is saturated, citrate will move out of mitochondria into the cytoplasm. In the cytoplasm, citrate is broken down into acetyl-CoA and oxaloacetate, and that acetyl-CoA in the cytoplasm is diverted into fatty acid synthesis. It is diverted into cholesterol biosynthesis. So that's how fructose, most of the fructose is converted into fatty acid and cholesterol in the liver. Now let's see what happens to the dihydroxyacetone phosphate in the liver. Now the dihydroxyacetone phosphate, it will be converted into glycerol 3-phosphate. Glycerol, alcohol, glycerol 3-phosphate. Dihydroxyacetone phosphate is converted to glycerol 3-phosphate. This job is done by glycerol 3-phosphate dehydrogenase enzyme. Glycerol 3-phosphate dehydrogenase enzyme, which of course uses NADH plus H plus, release NAD plus, all that. So dihydroxyacetone phosphate converted to glycerol 3-phosphate. Now this glycerol 3-phosphate, it will be used as a backbone to synthesize triacylglycerol. How that happens? So glycerol 3-phosphate, it means it has 3 carbons, glycerol 3-phosphate. The third carbon has got phosphate there. So you are synthesizing fatty acid from glyceraldehyde this side, you are making fatty acid there. So you bring that fatty acid, one of the fatty acid is attached to the first carbon, and then another fatty acid is attached to the second carbon, and then you remove this third carbon phosphate and add one more fatty acid there. So it means you get a structure something like this. 3 fatty acids attached to a glycerol 3-phosphate glycerol molecule, and this is called as triacylglycerol. So you are going to make triacylglycerol in the liver. And also the cholesterol can be attached with the fatty acid to make cholesterol ester. So most of the time what happens to your fructose that you consume along with the food, or maybe you eat sweet or in a dessert, or maybe drink a lot of fruit juice, or maybe eat a lot of fruits. During that time what will happen? So although each of them they have their own glycemic index, or interaction with the absorption mechanism can be different in each of them. So how much it is absorbed and metabolized. So most of the fructose that gets into the liver, it all floods into this direction and make fatty acids, cholesterol. Fatty acids are converted to triacylglycerol because you get a backbone from dihydroxyacetone phosphate becoming glycerol 3-phosphate, and may provide a backbone for triacylglycerol synthesis, and you make tags and cholesterol ester. What will happen to the tags? Initially this triacylglycerol and cholesterol ester, it will be loaded on to apolipoprotein B100. A protein in the liver is apolipoprotein B100. This apolipoprotein B100, it will be loaded with the tags triacylglycerol, it will be loaded with cholesterol ester, it will be loaded with phospholipid and vitamin E. So this entire molecule, we call that as VLDL, very low density lipoprotein. And that very low density lipoprotein, it gets into the blood, and blood levels of VLDL will be elevated, and most of the content in VLDL is tagged triacylglycerol. That is why consumption of more fructose, means eating more sugar, will increase tags levels in the blood, increase in triacylglycerol levels in the blood, and also to a certain extent it will increase cholesterol ester in the blood. Okay, so that's what happens with eating of lot of fructose here, because it floods into the pathway, although there is a rate limiting enzyme, but it is not regulated, and also the insulin is not going to regulate this particular pathway. That means fructose, it floods into this fatty acid synthesis, cholesterol synthesis, making tags. In fact, there are recent papers state that non-alcoholic fatty steatosis, especially in the diabetes patients, non-alcoholic fatty steatosis, NA, non-alcoholic fatty steatosis or fatty liver disease. Non-alcoholic fatty liver disease, one of the causes for non-alcoholic fatty liver disease is considered to be fructose, because it floods like this, and triglyceride can be accumulated in the liver, giving rise to fatty liver disease, which is other than taking alcohol. So because alcohol is a common cause of fatty liver disease, other than that, so still there are other factors that can give rise to fatty liver disease, and one of that is fructose, and that can give rise to non-alcoholic fatty liver disease. That can also, we can see. And also consumption of more fructose has been postulated to increase uric acid levels in the blood, especially in the diabetic patients. So these are some of the applied aspects with consumption of more fructose, and this is what is the fructose metabolism. You got to pay attention to enzymes here: fructokinase, aldolase B enzyme, glycerol 3-phosphate dehydrogenase, triacylglycerol enzyme, and the applied aspect. It means there will be a lot of VLDL synthesized, and it means more triacylglycerol in the blood, more cholesterol ester, and it can give rise to non-alcoholic fatty liver disease, increase in urate. And also there are two disorders that are associated with fructose metabolism. One is essential fructosuria, because of defect in. So if there is a defect in this enzyme fructokinase, so it will give rise to essential fructosuria. That's the disorder, genetic disorder. And if there is a defect in aldolase B enzyme, that can give rise to hereditary fructose intolerance. I'm going to make a video on these two disorders. So keep watching, and thanks for your time. So if you have any questions, so please don't hesitate to put that in the comment section below, so I will answer it as quickly as possible. See you in my next video.